Hello everyone, in this video we introduce cooperative consensus, the defining element of the Proxima project. Proxima is a novel layer 1 blockchain with unorthodox views on many things, including consensus itself. The cooperative consensus is fully permissionless, and it differs from the well-known blockchain models such as proof of work, proof of stake, or committee-based Byzantine fault-tolerant protocols. It realizes the 10-year-old vision of the tangle, a directed acyclic graph, or DAG for short, made of transactions instead of a chain of blocks. Despite this, the overall architecture of Proxima is simple and minimalist. Our goal is to present the entire architecture of Proxima step by step, and here we start with the consensus. The Proxima project is open source and already runs an open testnet. You are welcome to join, learn, and contribute. You can find all information starting from the Proxima GitHub resources. Now let's first revisit the general concepts and assumptions of decentralized ledgers. Here we are talking about an unbounded network of players, computers, called nodes. In general, we don't know how many nodes there are or who they are. Nodes communicate by exchanging messages through the gossip protocol, but communication is unreliable and comes with latency. Moreover, some nodes may be honest, while others may be malicious and pursue hidden agendas. The key property of this network is permissionless decentralization. Nodes come and go at own will, and it has no single source of global knowledge about the network state and no single point of failure. The main purpose of the network is to maintain a shared data structure, a distributed ledger. This ledger contains information about who owns which asset at a given moment, the ledger state, and it records all ownership changes, the ledger of transactions. Each node maintains its own copy of the ledger and its current ledger state. In an unreliable decentralized network, this means that each node may have its own view of the ledger and of asset ownership. To transfer an asset, the owner sends a transaction into the unreliable network. To keep all ledger copies consistent, nodes must reach a uniform opinion about the ownership of the asset by exchanging the transaction and participating in the consensus protocol. Reaching a consensus is a major challenge for an unreliable, decentralized network of unreliable nodes. There are many different approaches to this problem and different principles of consensus protocols. Before we jump into Proxima's cooperative consensus, let's quickly recap how blockchains work. Users send transactions to the network. Transactions reach mempools on nodes. Block proposers pick a set of transactions from their mempools, pack them into a block as a child of the previous block, and broadcast it to the network. Each new block modifies the ledger state. All nodes must apply the same blocks in the exact same order, otherwise their local ledger states will diverge. The global ledger state is defined by the chain of blocks. In most blockchains, the consensus problem is solved by selecting a leader for each step of the chain. In proof of work, the leading block is chosen through hash rate competition. In proof of stake, it is selected either by a committee or by a pseudo-random lottery. An exception is the block DAG of Caspa. Instead of selecting a single leader, all blocks are ordered based on the outcome of the hash rate competition. So most crypto ledgers follow a common architecture. Users send transactions to the network. Block proposers, miners, or validators pack transactions into blocks. These blocks compete or are selected by lottery. A chain of blocks is created, and it defines the ledger. The main idea behind cooperative consensus dates back to around 2015, when Sergei Popov, co-founder of IOTA, proposed a radical change to this traditional design. In his concept, blocks, block proposers, and their competition are replaced entirely by a new structure called the tangle. The tangle is a directed acyclic graph, or simply DAG, made of transactions, a transaction DAG. The original idea is that this DAG is built by the users of the system themselves. Cooperative consensus of Proxima takes this idea literally, realizing the original vision of the tangle. The tangle is built by a simple rule. When a user creates a transaction and wants to promote it to the ledger, the transaction must approve two other transactions that already exist on the tangle. This process produces an acyclic graph that grows continuously from the genesis as long as new transactions keep arriving to the network. The exact shape of the tangle may differ from node to node. because of network latency and message delays. We say that each user has a subjective perception of the tangle. Transactions that are not yet referenced by others are called tips. In general, transactions are not restricted in which ones they can approve, but the tips, as seen by each user, are the natural points for further growth of the tangle. It is up to the user which transactions to approve. Each user follows certain criteria or a strategy for selecting tips. Users naturally want as many others as possible to directly or indirectly approve their own transactions. Here we reach the key idea of the tangle. Each user wants the best possible future for their transaction, so they choose tips to approve in a way that makes their own transaction attractive for others to approve later. In mathematics, this kind of mutual decision-making is known as game theory. If the set of attractiveness criteria is aligned, the system reaches a stable collective behavior known as a Nash equilibrium. Simply put, by helping other users approve their transactions with yours, you help yourself. This idea lies at the core of cooperative consensus. Users take care of their own transactions and, by cooperating with one another, they achieve consensus on the ledger state. To reach a game-theoretical Nash equilibrium among many players in consensus on the ledger state, we must design strict rules of the game and the goal, the rewards for playing the game. In blockchains, protocol defines rules and rewards for block proposers, miners, or validators. They form a special category of participants who are paid for maintaining secure consensus on the ledger state on behalf of users that have their own motives to be involved. In Proxima, this category does not exist. There are no separate block proposers, only token holders themselves. So first, we must define moves of the game. That will be definition of valid transaction to be added to the tangle. Secondly, we want user to be actively involved into the tangle building, so we must provide rewards for that. The rules and rewards must be designed so that the game has an optimal strategy for its players, and the resulting behavior aligns with our design goals. In most existing blockchain protocols, the specific design of a transaction is orthogonal to the consensus. In Proxima, however, all main protocol constraints, including those related to building the DAG and defining rewards, are encoded as UTXO transaction validity rules. This approach is somewhat unorthodox, but it gives the Tangle protocol its minimalist nature. The validity constraints of transactions define the Tangle itself and determine the overall behavior of the system, leading to a global consensus on the ledger. Before looking at the bigger picture of the consensus, we first describe the transaction model of Proxima in more detail. Proxima uses an extended and programmable UTXO model for its transactions, which serve as the vertices of the tangle. UTXO stands for unspent transaction output. In the UTXO model, the ledger state at any given moment is represented as a collection of elements called UTXOs, or simply outputs. This collection is also known as the UTXO set. Each unspent transaction output is an asset recorded on the ledger. It holds a balance of fungible tokens native to the system. The UTXO itself is non-fungible because it has a globally unique identifier for its entire lifetime. It is also immutable, meaning it cannot be modified once created. A script attached to each unspent transaction output defines who controls it and under what conditions. The ledger state can change only by replacing some UTXO assets with new ones, producing a new ledger state. Only the owner can replace the UTXOs they control with new ones. Every mutation of the ledger must satisfy certain validity constraints that preserve key invariants of the system. One of the most important invariants is the scarcity of the total supply of fungible tokens on the ledger, a property that defines digital scarcity and the very purpose of the ledger itself. Let's say we have a particular ledger state. The only way to modify it is to apply a transaction. First, the transaction consumes specific UTXOs from the ledger state, called inputs. Those UTXOs are removed from the state. Second, the transaction produces new outputs that replace the deleted ones, creating a new ledger state. A transaction is a deterministic state transition. Its effect is known in advance. Each transaction must satisfy predefined validity rules that, among other things, preserve the invariance of the ledger. All unlocked scripts of the inputs must evaluate to true. The total balance of the inputs must be equal to the total balance of the outputs. Two transactions with non-overlapping sets of inputs do not interfere, and can update the same ledger state in parallel. However, two transactions that attempt to spend the same unspent transaction output are conflicting. They cannot be applied to the same ledger state together. A remarkable property of UTXO transactions is that non-conflicting transactions commute. The final ledger state will always be the same, regardless of the order in which those transactions are applied. A set of UTXO transactions can naturally be interpreted as a directed acyclic graph, with transactions as its vertices. We call it the UTXO DAG. The edges of the UTXO DAG represent the relationships between producing and consuming transactions. All transactions that can be reached along the edges from a given transaction back to the genesis form what we call the pass cone of that transaction. By definition, the pass cone of any transaction must not contain conflicts, meaning transactions that attempt to spend the same UTXO twice. There are two important properties of the UTXO DAG. First, the pass cone of any transaction is deterministic. It can be reconstructed in a unique and canonical way from the transaction set. Second, each UTXO transaction, that is, each vertex of the graph, represents a consistent UTXO set, or ledger state. That ledger state can be reconstructed in a unique way from the pass cone of the transaction by incrementally applying transactions starting from the genesis ledger state. It is important to note that the UTXO DAG in general may contain conflicting transactions, but two conflicting transactions can never appear in the same pass cone. Now for the final step, we add a special type of edge to the UTXO DAG called an endorsement. In addition to consuming the outputs of other transactions, a Proxima transaction can endorse any other transaction. The endorsement must not violate the acyclic property of the graph. The DAG with both consumption and endorsement edges is called the UTXO tangle. The extended UTXO tangle inherits the same properties as the UTXO DAG: deterministic pass cones and conflict-free pass cones. Each vertex of the UTXO tangle represents a consistent ledger state. The UTXO tangle is the structural foundation of the cooperative consensus. Proof-of-work blockchains are well known for their longest chain rule. It's the rule that defines how miners behave. We can say that the longest known chain is the most attractive option for miners to continue building their next block. Whenever a longer chain becomes known to a miner, they immediately switch and start mining on that longer chain. Following the example of the longest chain rule, we introduced the biggest ledger coverage rule for Proxima users. Just like in proof of work, the biggest ledger coverage rule guides a permissionless set of users toward consensus on the ledger state. Let's define by example a special metric called ledger coverage, or simply coverage. We start building the tangle from a given UTXO set. It can be the genesis of the ledger or a snapshot of the ledger state where the tangle begins. We call that UTXO set the baseline state. Here, the baseline state consists of 11 UTXOs. The sum of all token balances gives the total supply. In this case, 49 tokens. The coverage of a transaction is the sum of the balances of baseline UTXOs that are reachable in its pass cone. In other words, the number of tokens covered by that transaction's history. For example, transaction TX0 has coverage 10, while transaction TX1 covers 3 UTXOs with a total coverage of 12. Transaction TX2 consumes 1 UTXO produced by TX0 and 2 UTXOs from the baseline state. In addition, it endorses TX1. As a result, its pass cone covers 29 tokens in the baseline state. In parallel, transaction TX3 consumes a UTXO from TX1 and endorses TX0. It also consumes the same baseline UTXO already used by TX2. That double spend creates a conflict between the pass cones of TX2 and TX3. These two transactions will never appear together in any future pass cone. Now, the owner of an unspent UTXO, by spending it, faces a dilemma. Which transaction to endorse, TX2 or TX3? It can't endorse both since they are in conflict. The biggest coverage rule dictates that the token holder should endorse the transaction that results in the greater ledger coverage. In this case, transaction 2. Ledger coverage becomes a measure of attractiveness for other token holders who also want the best future for their transactions and seeking best options for cooperation. If for some reason a token holder issues transaction TX4 and it conflicts with TX6, then other holders, when facing the same choice, will endorse TX6 over TX4. As a result, TX4 and TX3 will likely not be endorsed by others and will become orphaned, meaning they won't make it into the consensus ledger state. Endorsing the transactions of other token holders is an act of cooperation. The biggest coverage rule defines the best way for token holders to issue and endorse their transactions. In Proxima, cooperative behavior is selfish. Each token holder takes care about her own holdings, yet it aligns individual incentives with the collective growth of the ledger. Let's look at the process of tangle building from the perspective of a node in the Proxima testnet, as shown by our first tangle visualizer. The tangle visualizer shows new transactions arriving to the node. Each transaction is a vertex of the tangle, and it naturally finds its place by bringing its own edges, the consumed and endorsed transactions of other peers. For now, let's not worry about why those transactions keep arriving, or why they appear in different colors. We'll return to that in later videos. Each token holder issues transactions by following the biggest ledger coverage rule. Every new transaction references other transactions that are close to the tips of the DAG. The newly arrived transactions represent the current moment of the tangle. Each one, for a short while, becomes a tip of the DAG until even newer transactions reference it. The constant flow of incoming transactions pushes earlier ones deeper and deeper into the past cones of the DAG. If we focus on a particular vertex in the tangle, we can see it slowly getting buried deeper into the past with every new tip that arrives. When a transaction becomes very far in the past with respect to the newest tips, it means that it almost certainly belongs to the past cone of every future transaction. In other words, being deeply buried in the tangle means the transaction has effectively reached its final confirmation in all future versions of the ledger state. Some transactions, however, fail to reach that stage. They don't make it into the past cones of future tips. They become orphaned or rejected by the network. As time passes, the network gradually approaches consensus on which transactions are final, based on how deeply they are buried in the shared past of the tangle. In the next video, we'll explore the topic of incentives. Why token holders continue issuing transactions, even when they don't intend to transfer ownership of their assets. We'll also look deeper into the concept of ledger coverage and how the system manages the ever-growing tangle while keeping the coverage metric capped. The answers to these questions, and many others, are encoded in the transaction validity rules, the very core of the Proxima architecture.